Okay, the second use of division is to find your slant asymptotes when you have a rational equation or a rational expression. That's where you have something like this. Like, let's say you had this, and you were asked to graph it. That would give you a slant asymptote, because remember, horizontal asymptotes only occur when my exponent up here is equal to this, or this is smaller than the bottom. So this has to be smaller than this to get a horizontal asymptote of 0, or they have to be equal. When the one on top is bigger than the one on the bottom, you're going to get a slant asymptote. And in order to find that, you have to divide the denominator into the numerator. Now, these degrees to do this for a slant will always differ just by 1, because in order to draw a slant asymptote, the ones you guys know how to do right now are linear, they're lines. So when you divide them, you have to have a difference of 1 degree. You won't have like a linear into a cubic, because that's not going to give you a line as the actual, when you divide it. So those are the different uses. Again, they're good for rationals when you need to find your slant asymptotes, and you'll also use it to break down polynomials. Number 4, you need to find your x and y intercepts, which I'm going to show you now. And it actually fits perfectly in with what we're doing right now. What I'm going to do is I'm going to show you a rational inequality. And one of the things that is important to understand is this is also going to show you how to solve a quadratic inequality, because this turns into a quadratic. And while I'm at it, I'll go ahead and talk about the intercepts. Okay, so what I'm going to do first is solve it as an inequality, and then I'm going to go back and graph it, because several of the things we need will come out of both, because it's the same equation. So let's say you're given 1 over x minus 3 plus 1 is greater than or equal to 6 over x squared minus 9. This is a rational inequality. And just like quadratic inequalities, you have to set it to 0. So you have to rewrite it as 1 over x minus 3 plus 1 is great. Oops, no, I want to get rid of that. Minus 6 over x squared minus 9 is greater than or equal to 0. Okay, now in order to put these together, you have to get a common denominator. I'm going to go ahead and change this. Instead of x squared minus 1, that is a difference of 2 squares. So that's going to become x plus 3x minus 3. Okay, so this is the difference of 2 squares. I'm going to factor. My least common denominator has to be something that includes both of these. It has to have an x minus 3 in it, and it has to also have any other factors in the denominator. And this one has an x plus 3, so I have to throw that on. So this is something similar to what you've seen before when we were just adding rational equations, rational functions, which is why you had to learn to do that, so we can do this now. So this has the x minus 3. It doesn't have the x plus 3, so I'm going to have to take the 1 x minus 3, and I'm going to have to multiply it top and bottom by what's missing, which is the x plus 3. Okay, and then plus 1, well, 1, that's missing everything, so we got x minus 3, x plus 3 over x minus 3, x plus 3, because it had no denominator, which is 1. When you divide something by itself, you have 1. It's just rewritten and manipulated. The 6 has everything. The 6 has all of the denominator already, so I don't need to fool with it, and that's greater than or equal to 0. When I turn this into one giant fraction, I end up with, make sure this is being recorded, yeah, I end up with 1 times x plus 3 minus 3, which is going to give me just x plus 3, plus, when I multiply x minus 3 times x plus 3, I get back x squared minus 9. That's where it came from. That was the difference of 2 squares. Minus 6 all over x plus 3, x minus 3. I want to keep this factored because I need to find the domain. Okay, so as in all rational equations, it's very important that you mark down your domain. The domain restrictions in this case, it's going to be defined to be x, where x, and this is how we write it, is an element of the reals, but x can't be 3 or a minus 3. So the two things you can't have be part of your answer ever is a minus 3 or plus 3, because those are probably going to be vertical asymptotes. We'll see in a minute. If they end up canceling out, that means they're a whole, but we don't know that yet. Okay, so when I combine that, I get x squared plus x minus 12 all over x plus 3, x minus 3, and that's all greater than or equal to 0. this is going to be the function, the expression I'm going to be referring to. This is the inequality. I'm not going to even fool with this one anymore because this wasn't in a form I could use. So this is the inequality I'm going to be looking at to finish this, all right? So from now on, I'm going to refer to this because it's in simplified form where I can see it. Okay, and this is whenever you're looking for, what you're looking for, whether it's above, remember this is a greater than 0. So what you're looking for is you have this x-axis, and you want to know when is it above the x-axis or when it is below the x-axis. When it's greater than or equal to 0, it's on or above. So the only part of that that makes any sense is just the numerator. It doesn't make any sense to set the denominator equal to 0 because that will just give you vertical asymptotes. So we have x squared plus x minus 12 is greater than or equal to 0, and that's the only part we're interested in, as I said. So in order to solve this inequality, a quadratic inequality, I'm going to have to see if I can factor it, which would be really nice if I can. And sure enough, I can. Factors of 12 that subtract to a positive 1 would be a 4 and 3. So that works. So x plus 4, right? And x minus 3 is greater than, equals 0. Okay, that's the next thing. I almost forgot. When you solve these, you don't solve them as inequalities. You solve them as equations because you're looking for the roots, and the roots are when they're equal to 0. When we go over here and draw this, we're going to be looking for when we're looking at when it's greater than 0, when it's equal to 0, and when the y, this is y, I shouldn't have said equal to 0. On the x-axis, y is equal to 0, and then when y is less than 0. So we want to set it equal to 0 to find out where our roots are. So we have x equals a negative 4, and 3 is when it's 0. Now, at this point in time, you need to check because this is a rational equation you're working with. It's not a quadratic by itself. It started as, I mean, we're just looking at the top, which is quadratic, but the whole thing is irrational. And you'll notice that this cannot be used because that happens to be an asymptote. So the only actual x-intercept I've got is 4, a negative 4. So now what I'm going to do on this graph is I'm going to go ahead and mark all the critical values, the parts that are interesting. My asymptote at a negative 3 is because the graph could change from lower to higher when it gets on the other side of the asymptote. I have an x-intercept. I should have started with 4. Let me start with 4 so I have more room. Okay, so I have a negative 4 as my intercept. Okay, that's an actual x-intercept at a negative 4. All right? And then the graph has an asymptote at a negative 3. And it has another asymptote at 3. Let's see if that's right. Did I do that right? 4, 3, yes. Okay, so those are all the interesting points where something could happen. It could go above or below the x-axis. I probably shouldn't have drawn that so big so I have more room. Okay, so we'll do this here, and we're looking for above and below. So this is an asymptote at 3. Okay, so let's go ahead and do some test points. Let's pick some test points. We'll do a negative 5 as a test point. 0 is an easy one between negative 3 and a 3. Between 4 and a negative 4 and a 3 is a negative 3 and 3/4. All right, and then something on the other side of 3, which since it's an asymptote I need to do over there, we'll do 4. So those are going to be my 4 test point places. Now, when I do test points, I want to actually go back into the inequality. I'm actually looking at the rational inequality when it's greater than or equal to 0. I just looked at the numerator temporarily to find the intercepts. But I'm testing the whole entire rational equation, not just the intercepts. I'm testing the rationals too. So what I'm going to do, and I like to do, is I like to rewrite this so that I have it in complete factored form. You'll notice the numerator was factored right here, x plus 4, x minus 3. And then I have the denominator factored as well, which was x plus 3, x minus 3. Now what happens is I don't need to worry about that because anything I plug in is going to come out exactly the same. So my test points, I have to plug back into my original equation to see whether they give me a positive or a minus. I can't plug them just into the quadratic because that's not actually the full inequality. So let's try the negative 5 first. If I plug a negative 5 in here, Again, I'm going to do a negative 5 plus 4, and it's just easier. You could have plugged into this right here, but then you have to square and stuff. This is exactly the same as that. These are identical inequalities. They're the same thing. They're both the same rational equation. One's just factored, and it's easier for me to work with factors. So I usually go ahead and just write it out in factored form. So negative 5 plus 4 is a negative 1, and negative 5 plus 3 is a negative 1. I'm not a negative 1. I'm just putting negatives down. I don't care what the numbers are because those are irrelevant. This is a negative. This is a negative. Two negatives make a positive. So I know over here I am above. When I'm over here on this side of 4, I'm at a positive, okay? So I'm assuming when I cross at negative 4, I'm going to go underneath it. So let's try some. We're going to try a negative 3 and 3/4, which once again is easier to use in the factored form. So negative 3.75 plus 4 over a negative 3.75 plus 3 gives me, this is positive, this is negative, so it's negative. So evidently I crossed underneath the x-axis when I got past 4, negative 4. Let me put that over here so it's easier to see. Okay? Then I want to know what happens at 0. 0 plus 4 is 4. 0 plus 3 is 3. That comes out to be positive when I plug 0 in. I'm plugging in right here. When I plug 0 in there, I get a positive, so I know my graph is above the x-axis on that side. And now I need to plug 4 in, which was my test point. 4 plus 4 is 8. That's positive. 4 plus 3 is still positive. Positive and positive gives me a positive. So apparently it stays above the x-axis once I cross. That's interesting. Well, anyway, so my answer, assuming I didn't make a mistake, that seems weird. It seems like I should go back underneath. As a matter of fact, I'd be willing to bet money it's supposed to go underneath. That's a positive 4 plus 3 minus 4 plus 3 is 7. 4 minus 3 is 1. That's going to be negative. Oh, that is going to be negative. So I've done something wrong. This should be a negative. I'm looking at the original equation trying to figure out what I did wrong. If I do it up here, 4 squared is 16 plus 4 is going to be bigger than a negative 12. So the top is going to come out positive. If I take 4 plus 3, I get a plus. Oh, no, 4 minus 3 is a plus. That does, and it still comes out positive. Okay, this must be a positive. Assuming I wrote it down right from the other side, that is correct. Okay. So anyway, that's what it looks like. So to answer the question, if you go back, it was asking when it's greater than or equal to 0. Well, that's going to be from here to here and on the x-axis. So you would have to write, let me go ahead and erase these so I have a little more room for writing down the inequality. You would go when it's greater than or equal to 0, it starts at a negative infinity. Here's the first spot where it's greater than 0. And then at a negative 4, it stops. And the negative 4 is an intercept. So it gets a square bracket because I'm looking for when it's greater than or equal to 0. And it's equal to 0 when it's an intercept. Okay, then up here it goes above again here. And you can't include the asymptote because it's nothing at the asymptote. So the first asymptote, this was a negative 3. This was a positive 3. So it goes above again at a negative 3, which has an open parenthesis because it can never be included. The asymptote can't. And then an open parenthesis at 3. And then you have to jump over 3 and infinity, okay? So that would be your final answer. I kind of ran out of room there. But that's what you're looking at. So I feel like there's something, I messed something up because this seems weird that it would stay above the x-axis, but maybe, I don't know, I'm iffy. I'm very skeptical about this, but it is what it is. I just plugged this into my calculator and I see where the problem is, why it ended up staying up. That is actually correct, but I can tell you why that worked. And hopefully some of you were looking at this going, but wait, isn't that a hole? And the answer was yes, if that's what you were thinking. I forgot something that I just got done saying in the other video. Okay, what I want to point out that's critically important, and actually you learn most from your mistakes. So this mistake will stick in your head and hopefully you won't forget not to do this. The x minus 3 and the x plus minus 3 on the top and the bottom crossed out. Remember, when you're able to reduce a domain restriction of x minus 3, when you can cancel it out so your final answer doesn't include it, that is not an asymptote, that is a hole. So at x equals 3, I don't have a vertical asymptote, which makes perfect sense now, because that graph, usually asymptotes, when you have two of them like that, the graph will flip to the other side. So I was having a really hard time believing that was right, which is good because my intuition said this cannot be right. 3 is not an asymptote, 3 is a whole, because it reduced with a numerator. So it makes perfect sense that it stayed above because it never crosses. What happened is the graph would have done something like this, had a hole here, and then it kept going down. You know what I'm saying? So it was asymptotic on this side, but then it never actually crossed again. It just had a hole right at 3, but it stayed above, which is perfectly consistent. So that won't really change my answer because I have to stop at the hole. It's not an asymptote, but I still can't include it. So it would still be a minus infinity to a negative 4 square bracket because it's included. And then it would still start at a negative 3 with round brackets because it's an asymptote. You can't include it. And it would have to stop at 3 because 3 is a whole. So there is no y value there. So you can't say it's going to exist. And then you jump over that hole and you go on to infinity. So my answer would have been the same. It's just now I can make sense of it because before I was thinking there's no way that's going to do that. So that's why it's a whole. So remember, if your denominator cancels with a factor in your numerator, that's still a domain restriction, but it's not an asymptote. It is it's a whole. Okay. So that's a lot of work. You can watch this video 10 times and walk through it. Everything I did was correct. It was just the interpretation of this domain restriction saying that was a asymptote. It was actually a whole because it canceled out. But the rest of it is the same. It's just knowing what to do when that canceled. The one thing I wanted to do now was actually graph this because I have all the information I need to actually draw a graph. When you graph, and I just want to make sure you guys are clear since we've gone through all the trouble of getting that information. When you graph a rational function, you need to, and I put this on the other board, but I'll put it down again, you need to know your x and y intercepts, and you need to know any asymptotes, and then test points. And we have already, test points. Okay, so we have actually already gotten all that stuff, so I'm going to go ahead and show you how you would finish graphing it. So I'm going to go ahead and make a graph here. Okay, so we know we have a hole at 3. I'm not going to draw that in yet. We know we had a vertical asymptote at a negative 3. X equals a negative 3 was a vertical asymptote. I know that I have an x-intercept. I believe that was at a negative 4, right? When I set the numerator equal to 0, which if you're asked for the x-intercept, you set your numerator equal to 0. And there was what I got when I had the numerator equal to 0. It gave me negative 4 and 3, which 3 was the whole. X-intercept was equal to negative 4. What else did I have? Okay, so I don't have my vertical and my horizontal asymptotes. So I'm going to go back here and grab this and write it down. It was x squared plus x minus 12. Okay, so it was x squared plus x minus 12 over x minus 3, x plus 3. Okay, so I've got my x-intercept. My y-intercept is always going to be really easy to find. The y-intercept is when x equals 0. So if I let x be 0 over here, I get a negative 12, because 0 squared plus 0 is just 0. 0 minus 3 is a negative 3. 0 plus 3 is 3. Negative 3 times 3 is a negative 9. Is that right? 0 minus 3 is 0 minus 3, yeah, plus 3. It's a negative 9, which reduces to a negative 4 over 3. A negative 4/3 is negative 1 1/3. So I have y-intercept at a negative 1 1/3. That's supposed to be positive. Ooh, my bad, sorry. Goodness, I'm having all kinds of issues here. So let's get rid of that because that's not right. I was just thinking that doesn't look like the way we had it originally. So 1 1/3, it's a positive 1 1/3. Sorry about that. If I confused you, I didn't mean to. Negative over negative is a positive, yes. Okay, so it's a positive 1 1/3. And then the last thing I need to know is my horizontal asymptote, okay? Now this is where you remember, if you FOILed this you would end up with x squared as your highest power. These two would give you x squared. Your highest power on top is x squared. Remember, when your horizontal asymptote comes when your powers are the same, you take the coefficients. Well, the coefficient of that is 1. The coefficient of that is 1. The x squareds cancel, and I just get 1. So my horizontal asymptote is y equals 1. Okay? So at y equals 1, I have a horizontal asymptote. So let me go ahead and draw that. And then I've already done the test points, which I had to do for over here. I know the graph is above over here, it goes below, and then it stays above from there on off. So in order for it to be above the graph and then go below and stay in line with the horizontal asymptote, it must look something like this. It must go like this. Okay? Because you wanted to scrape the horizontal asymptote and go from being above to below. And then the rest of the time it was above the x-axis, and if it's going to be going toward the horizontal asymptote, that means, and again, if it's going to be scraping the vertical asymptote and going next to the horizontal, it must have done something like this. Now remember, at 3, I'm going to go ahead and erase that and put that below so that... Okay, so at 3, I had a hole. I don't know why I'm dotting that. So that's what the graph would look like right there, because I had all the information I needed. So I'm just doing this to kind of showing you how to, how you use this information. Your vertical asymptotes, or in this case a hole, you have your x-intercept, your y-intercept, and then you have your horizontal asymptote, which was equal to 1. And that's actually y equals 1, not the horizontal asymptote is y equals 1. Okay, and that's how you would go about graphing that. And that's about all you can do with rationals, and that's a lot, I know. So you kind of have to keep in mind what you're looking for. The key part is remembering rational equations have asymptotes, horizontal and vertical, or slant. Sometimes they don't have a horizontal, they have a slant. They have vertical asymptotes, or they could have a hole. So you have choices of what you find. You can have a vertical asymptote or a hole. You can have a horizontal asymptote or a slant asymptote. Okay, I guess I could have put SA. You can have you're going to have a y-intercept unless your horizontal asymptote is x equals 0. Now, the only time you won't have a y-intercept is when your horizontal asymptote is on the y-axis. Then you obviously can't have a y-intercept. Otherwise, you will have a y-intercept. And you don't necessarily need to have the x-intercept. You may or may not have if the graph is like this. Let me draw this real quick. I've seen graphs like this that look like that, and then they look like that. So they never actually cross the x-axis. So you don't have to have an x-intercept, but for the most part, usually the ones we'll be working with will. And once you have that information, all you need to do is test points, all right? So you need to find your critical numbers and then do test points. Okay, so test points are the last thing. As far as solving a rational inequality, it will involve, I'm going to put rational inequality. You need to find your vertical asymptotes or your hole when you're looking for a rational inequality, and you need to find your x-intercepts. That's all you care about, because all you're looking for is places where the graph could have jumped from above to below. And that's only going to happen at asymptotes. Well, actually, it won't happen at a hole. You don't even care about the holes. And then it's going to also you do care about the holes. It's a hole, or it's going to happen at an intercept. So those are the only things you need to know about when you're doing a rational inequality, is these two things. Everything else is only needed if you're going to graph the whole thing, or if you're being asked to find the slant asymptote. The y-intercept doesn't really, and then I guess you need to do test points. The y-intercept doesn't count when you're doing, or it's not necessary when you're doing an inequality.